On behalf of the Department of Mathematics at Princeton University, it's my pleasure to welcome you to the third Minerva Lecture series. And before Professor Bhargava introduces Professor Terence Tao, I'd like to say a few words about the Minerva Lectures. So the Minerva Lectures are funded by the Fernholz Foundation, and the Fernholz Foundation was graciously and generously set up by Louisa and Robert Fernholz, and directed by Louisa Fernholz. And the Fernholz also actually endow the Minerva Foundation, which has been long-time generous supporters of the math department. So I'm very happy to recognize their generous contributions. So it's my great pleasure to welcome Professor Manjul Bhargava, who will introduce our Minerva speaker.
Thanks, Dave. And I want to join Dave in thanking again the Minerva Foundation and the Fernholzes for their generosity in making these Minerva Lectures possible. Their help has really helped make this department much more active and made a big difference in our activities in the mathematics department. So thank you again to them. So it's just a great pleasure to introduce my longtime friend and inspiration, today's speaker, Professor Terence Tao of the University of California at Los Angeles. So when Dave asked me to do this, I was wondering how I could possibly say something about Terry's mathematics in a couple minutes. And then I was looking at what I had prepared to say about our first Minerva speaker, Professor Sayre, and realized that what I wrote for him also applied very well to Terry. So here's what I said about Professor Sayre. So you can see that, and you can see my laziness as well. No. Our speaker today has been a major source of inspiration for scores of people in this room. His transformational contributions to so many areas of mathematics are discussed in our department, and his prolific writings are read by our department members pretty much every day. I won't go into the list of the highest honors and awards that our speaker has received, because if I did, that would take up the entire hour. Instead, what I want to say is that what impresses me most about the speaker, it's kind of amazing, it's all the place, is that not only is he one of the most prolific mathematicians of our time, but that he also has an unwavering commitment to mathematical exposition and to the dissemination of mathematics. His writings are crystal clear and super enlightening, and he works magic with his chalkboard and blackboard when he lectures. Anyway, that's what I wrote for Professor Sayre, and as you can see, it applies. It applies just perfectly to Terry. Of course, Terry is slightly younger than Professor Sayre, which makes it more amazing. All these things are really true about him already. As I said, Terry's made transformational contributions to numerous areas of mathematics, including analysis, combinatorics, number theory, geometry, and the list increases every day. So check back tomorrow. And you'll get a feel for this range of topics inherent in Terry's work as you see Terry's lectures this week. So finally, on a more personal note, Terry is also incredible as a person and a wonderful friend. One of my favorite trips as a tourist was when we toured Paris together a few years ago. And so we toured the Louvre and visited the Arc de Triomphe, and then did some nice mathematics at the top of the Eiffel Tower. You remember that? So that's what knowing Terry is like. And for all of these reasons, I can't think of a better person to end our inaugural Minerva Year Lectures this year with. So please join me in welcoming our third and last Minerva speaker of this year. He'll speak on sets with few ordinary lines. Professor Terence Tao.
Thank you very much for that amazing introduction. It's never been compared to Sayre before. That's really quite an honor. And it's great to be back here. I was here as a graduate student for 4 years, and it still feels like home. Nothing much has changed. Even the snow looks the same. Okay, so I'm giving 3 talks, and they're on fairly different topics, but the first 2 talks are sort of loosely connected in theme. They concern a trend which has happened in the last few years in combinatorics, especially incidence combinatorics. which is a loosely defined subject, but basically counting things involving points and lines and circles and polynomial curves and other sort of geometric objects and how they intersect each other. So more and more, we've been getting a lot of progress on instance problems, long-standing problems in instance combinatorics, using techniques both in algebraic geometry and also algebraic topology. In a sense, it's not that surprising in retrospect that these tools are useful, since instance combinatorics is the study of geometric objects which are defined by which are algebraic curves. So it's not so surprising that the algebraic tools are useful, but there's been really dramatic progress in solving problems that were considered almost intractable by other means, and now we can attack them by these tools. Generally speaking, if your problem is over a finite field, then algebraic geometry methods seem to work well, and if they're over the reals, then a combination of algebraic geometry and algebraic topology methods seem to work. So there's many examples of this now. There's two that I won't discuss today, but probably the most striking is about 2008, I think. Steve Advier was here at the Institute, proved the finite field Kikeya conjecture. Using tools from algebraic geometry, which was a big surprise. And then a few years later, another nice result, which is by Larry Guth and Nats Katz, who almost proved the Erdős distance problem, who almost solved the Erdős distance problem. It's the smallest number of distances you can form with endpoints in the plane. They got a bound which is within a square root of logarithm of optimal, using tools from both algebraic geometry and algebraic topology. So I won't talk about these two, but I'm going to talk about two other results of this flavor where methods from algebraic geometry and algebraic topology are being used to prove things in combinatorics. Today I'll be talking about a fairly low-tech application of algebraic geometry and algebraic topology. The algebraic topology will come in Euler's formula. And algebraic geometry is the classical 19th century algebraic geometry of cubic curves. So curves of degree at most 3. So not very advanced. The next lecture will have a slightly more advanced algebraic geometry, 20th century SGA coming in. But this is more classical. This is the joint work of Ben Green. Okay, so this is a talk about lines, points and lines in the plane. So let's start with a definition. So suppose that P is a set of endpoints. So let P be a set of endpoints in the plane. Finite set of points. Okay. So then you can start connecting these points by lines, and we make some definitions. We say that a K-rich line is a line in R2 in the plane that is incident to, that contains exactly K points from P. Okay, so this is a 3-rich line, this is a 2-rich line, and so forth. And then with an n sub k, be the number of k-rich lines. Now, this is only an interesting concept for k because of n equal to 2. Of course, you have infinitely many 1-rich and 0-rich lines. Okay, but it's the 2-rich lines and higher which are finite. And so the questions we're going to be, and when k equals 2, so if you pick endpoints generically, you expect most there to be a lot of 2-rich lines but no higher. So we will call it an ordinary line. So a 2-rich line is also called an ordinary line. Okay, so this is a very classical topic, ordinary lines, and one of the first theorems in the subject is a very famous one called the Sylvester-Galai theorem. So this was posed as an exercise, as a problem by Sylvester in 1893, but the first published proof actually appears in 1944 by Galai. So the claim so the theorem is that there's always at least one ordinary line, except in one exceptional case when if all your points are collinear, then of course you don't get any ordinary lines once you get 3 or more points. So if if the points in P is not if the points in P. then there exists an ordinary line. Okay, so N2 is at least 1. Okay, so this is a great theorem. Maybe just to point out that this theorem is not entirely trivial, it's important that you live over the reals. If you replace the reals by other fields, this is not true. So this is not true. Okay, so for example, if you work with a finite field, F mod P, say, you could just take P to be everybody. You could take the entire finite field. As long as P is at least 3, then it's easy to see there's no ordinary line, because every line is P-rich. A less trivial example, if you work in the complexes, complex plane, then there is an example called the Hasse configuration. Which has 9 points, not collinear, and no ordinary lines. So the way it works is that in C2, what you do is that you make an elliptic curve. And in C2, elliptic curve look like tori, if you squinted it the right way. And what you do is you take the 3 torsion points. So it's a group. You take the points of order 3 in your elliptic curve, and those are 9 points, Z3 equals Z3. And because 3 points in an elliptic curve add up to 0, if they're collinear, you can quickly see that every line that hits 2 of these points hits a third. In fact, this has the geometry, I think, of the final plane. So that's an example where it fails. So if you want to prove this theorem, you must use something about the real line, which the finite fields in the complex field don't have. So you have to do something slightly non-trivial. Now, the standard proof is a beautiful proof. You've probably all seen it before, but I want to give it again just because it's so pretty. So the standard proof of the Sylvester Lie theorem is that what you do is that you consider lines which are at least 2-rich and points. So every time you have a rich line, because the points are not collinear, there must be at least one other point not on that line. And then so that point is some distance away from your rich line. So for all pairs of rich lines and points, you find the pair that minimizes the distance. Okay, so there's a finite number of points, so you can eventually find a point P and a line L which minimizes this distance. Okay? And so you've got a point, and you've got a line which is really close, but not on the line. And if this line is too rich, if this line is ordinary, then you're done. Then you have an ordinary line. If it's not ordinary, then there's at least 3 points on this line. So 2 of them are on one side of this perpendicular, or maybe one is actually on the perpendicular. It doesn't really matter. But 2 of them will be say on the right side of this perpendicular. And then it's easy to see geometrically then that this point is closer to this line than this point is closer to this line. This is a contradiction. Okay, or if you like, this sets up an infinite descent. So this is the standard proof of the Sylvester Lie theorem. And, it's very short, very beautiful, and it very much uses the properties of the real line, in order to minimize distance and so forth. And to talk about left and right, that's very much something that only the reals can do, or the rationals, or things in the reals. Okay. But that proof is somehow it's too clever. It doesn't seem to extend to do other things other than prove the Sylvester Lie theorem, unfortunately. But it is very pretty. But anyway, once you see this theorem, if you do instance combinatorics, it's then natural to ask. Okay, so then the question is, what is the minimal value? N2 for fixed n with the endpoints not all collinear. Okay, so if you have n points, not all on one line, Sylvester Lie says there's at least one ordinary line. But the question is, how few ordinary lines can you make? Of course, you can make a lot of ordinary lines. If you take the endpoints to be generic, you should get n choose 2 ordinary lines. You can get every line pretty much with 2 points ordinary. But the interesting question is, what's the minimal number? Okay, so there's there's some basic counterexamples. So Brodsky, which I can't spell for some reason. Okay, there is this, okay. Brodsky gave the following counterexample. So first comment, this problem is set in the affine plane, but without loss of generality, and it's actually a little bit more natural to put it in the projective plane, because this question is invariant under projective transformations that preserves lines and so forth. And if you're on the projective plane, which is the plane with the line infinity, you can apply a projective transformation, move all the points on the line infinity off the line infinity. So without loss of generality, we can work in the projective plane. That's a bit more technically convenient, as it turns out. So there's a standard example that suggests how low you can go. If n is even, what you can do is you can take the unit circle, and you can take n over 2 equidistant points in the circle, like the n over 2 roots of unity, if you will. And then they create all these chords. And then at the line infinity, which I sort of draw over here, you take all these chords and you see where they hit. And there are n over 2 places where these chords can reach. I guess you also have to include the tangents as well. And so these n over 2 sort of roots of unity at infinity. And if you do the computation, so together they form endpoints in the projective plane, which have only n over 2 ordinary lines. Of course, most of the chords here will hit a third point infinity. The only lines that are ordinary are the ones that are tangent to one of the points at the sphere. And that creates n over 2 ordinary lines. So given when n is even, you can create n over 2 ordinary lines. When n is odd, you can't quite do this. But you can add or remove a point on this line or this circle or throw in the origin. And you do the computation, you can get a similar example with basically 3/4 n ordinary lines. Okay, so this is a configuration with very few ordinary lines. You can get slightly fewer than this for very small configurations. If you take a triangle and its midpoints and a centroid, this is a configuration with seven points and only 3 ordinary lines. Okay, these 3 lines are the ordinary lines, and that's slightly less than these bounds here. And then there's a more complicated configuration, which I won't draw, which is n equals 13 and 7 ordinary lines. That's not right, 6 ordinary lines. Which is also slightly lower than these bounds. And so the conjecture was that these are sharp. So in particular, once you get more than 13, and if you have endpoints not all collinear, then the number of ordinary lines should be at least n over 2 when n is even, and 3 n over 4 when n is odd. Okay, but these configurations should be the best. There's a general principle in this subject that sort of algebraic configurations, things that sort of come from some very symmetric algebraic object, tend to give you the minimal configurations, although actually proving that is often a challenge. So this was the conjecture. There was so there's a lot of partial progress on this conjecture. So as I said, Sylvester Galai gives you that n over 2 is at least 1. In what year? Sorry. In 1940, Melchior gave another proof of the Sylvester Galai theorem that shows that, in fact, n2 is at least 3 for n bigger than something, n bigger than, I think, 3. Now, this may not look like such a great improvement, but his proof is much more robust than the proof I just gave, and that's important. And then there's some other work. Okay, so in 51, Motzkin showed that n2 must grow like at least the root of n. In 58, Kelly and Noza showed a linear bound for the first time, which is 3 n over 7, which exactly matches this first configuration that I said here. And then until recently, the best bound was in 73 by Seamer and Sawyer, show that n2 is bigger than 6n over 13 if n is at least 7. Okay, so getting close to n over 2, and again, that bound is tight because of this other example that I didn't draw. Okay, so what Ben and I did was we proved this conjecture for n large enough, okay, that for n sufficiently large, n2 is at least n over 2 for n even. Okay, and yeah, for n points not all collinear. Okay, so we can actually prove this conjecture at least for n large enough, which in principle leaves the rest of the conjecture as a finite check. Unfortunately, n large enough for us is 10 to the 10 to the 10, so we can't actually settle the problem. But asymptotically, at least, we do have a result. Okay, so all right, and this you'll see the algebraic geometry come in the proof. You already saw just a hint of it with this elliptic curve construction. In fact, you know, if you look carefully, this is also a cubic curve here. This circle and line. It's also a cubic curve. There are cubic curves all over the place. It's not initially obvious because it's a question about lines. Where do the cubic curves come from? And that comes from a very classical theorem in algebraic geometry, the Cayley-Bacharach theorem. So I'll talk about that later. But let me just okay. So before I go on to talk about how this theorem is proven, let me one of our other results. There's another result which was very closely related to this one, which is another question of Sylvester, where you don't talk about n2, you talk about n3. Okay. The maximum. Okay. So this is called the orchard planting problem. So given n points in the space, how many 3 in a rows can you make? Okay, what's the most number of 3 in a rows you can make with fixed n? Now here you don't need to make the n points non-collinear because collinear is not a very good choice to make lots of 3 in a rows. And you want to maximize. Of course, you can minimize very easy. You can easily have configurations with no 3 in a rows. Okay, but you want to maximize the number of 3 in a rows. So there's a trivial bound. So if you double count. Every pair of points in your configuration must lie on some k-rich line, and every k-rich line has k choose 2 pairs of points. So you do have this bound, which tells you an upper bound. N3 is at most 1/3 of n choose 2. Okay. So you can't have much more than n squared over 6. In fact, you can't have close to n squared over 6 triples. But you can come very close to that. And again, using an elliptic curve. So for the counterexample, if you let say C be an elliptic curve, something like y squared equals x plus ax plus b. Okay, so. Okay, so if you have an elliptic curve, then it's well known that elliptic curves, points on an elliptic curve form a group. There's form an additive group, and 3 points on the curve sum to 0 if they lie on a line, if they're collinear, if and only if. So what you can do is that you get in an elliptic curve, you can take a subgroup of order n. And a real elliptic curve, it either, as a group, it's either the torus or 2 copies of the torus. So you can always find a group of order n for any n. And then so there's lots of triples in a subgroup of order n that sum to 0, and you can just compute it. And you find that in this configuration, the number of 3 rich lines you can get is n minus 3 over 6 fraction of power plus 1. So that's n squared over 6 minus n over 2. the bounded error. So you can see that elliptic curves come very close to saturating the trivial bound. Almost every line that goes through 2 points goes through a third. There's only a few points that don't, and those are the lines that are tangent to 1 point and hit another. You can modify this example just by a little bit. You can also look at a coset of an elliptic curve. You can translate it by an element whose triple is back in this set. So there's like 2 other cosets of every subgroup, which also give you this construction. There's also a degenerate case where you take what's called an acnodal, a cubic curve. It looks a bit like this. So it's y squared, for example, y squared equals x squared, x cubed minus x. It's a good example where this loop here has shrunk to a point. And now this part is still has a group structure, and you can take a subgroup of endpoints over here, and you can still the plus is a point infinity, and so you can still generate the same example in this degenerate case. Okay, so this is a construction that that almost saturates the trivial bound, and we were able to prove that this is actually the best possible for n large enough. For n sufficiently large, this bound is the best bound. Okay, the elliptic curve example cannot be improved. Okay, so so these things look a little strange because the extremal configurations, they have this cubic structure, right? And the original problem just has these points and lines. So the way we prove this, these 2 theorems, they're both consequences of another theorem. Actually, I guess I have a second board here. No, let's go back. Okay. So the first observation is that if this bound were not true, if you had even more free-rich lines than the elliptic curve counterexamples, then there'd be so many free-rich lines that there's not enough room for the 2-rich lines. Then you can show that the 2-rich lines can't go much bigger than some constant multiple of n. Okay, and that just follows from computing with this trivial identity here. So if you had a counterexample to this theorem, then you'd have a set with very few ordinary lines and just a big n ordinary lines, which is not expected. If you take n points in general, you get n squared ordinary lines. This is a set with very few ordinary lines. And similarly, if you have a counterexample to this theorem, if n2 was less than this, then of course clearly n2 also would be big over n. So our approach to these 2 problems was not to look at the actual conclusions, but just to study those configurations that have few ordinary lines. And this is a type of strategy that's proven very useful in combinatorics recently. That if you want to study some statistic, which is generally very large, but occasionally very small, trying to classify those sets for which some sort of statistic measuring structure is very small, often you can get a very good classification. And if you get a good enough classification, you can then solve a lot of problems relating to that regime, where, in this case, the regime where we have few ordinary lines. So our main theorem, which implies the other 2 as corollaries, is actually a classification of sets with few ordinary lines. So our main theorem, so a structure theorem, it basically goes as follows, that if n is sufficiently large, and you have few ordinary lines, let's say less than kn, and k in our problem can go up to log n to a small absolute constant. And it's because of log, this is why we need these 10 to the 10 to the 10 sort of things, unfortunately, in our theorem. But for k, which is asymptotically is allowed to be somewhat large, if you have a set of few ordinary lines, then after adding and deleting, big O k points, and applying it a projective transformation, your set P is one of the configurations previously mentioned. So the configurations previously mentioned are, well, there's one case where all the points are on a line. That's one configuration with very few ordinary lines, in this case none. Another configuration was the circle and the line infinity, and over 2 points on each. And then the third configuration, then there's two other configurations, one coming from finite subgroups of a Algebraic curve and the cosets, two other cosets, and finite subgroups of this actinodal cubic curve. Okay, and these turn out to be basically the only configurations that have few ordinary lines. You can only do a few number of things to them. You can projectively transform them around. So like you can turn the circle to an ellipse, for example, or some other conic. And you can take these cubic curves to not be in Weierstrass form. You can have any old cubic curve. And you can add or remove a few points, but every time you add or delete a point, you tend to create about n ordinary lines when you add or subtract a point. So after adding or deleting about big O of k points, you start getting too many ordinary lines. But this is basically a complete, asymptotically, this is a complete classification of sets with few ordinary lines. And then once you have this, the other results are basically just somewhat tedious case checks to show that among all configurations in this class, the minimizers are what we said. Okay, so, oops. Okay, so this is our main theorem. So to explain how we prove it and where the algebraic geometry and the algebraic topology comes in. So let me first recall Melchior's proof that there's at least 3 ordinary lines. So it's also a very nice proof. It's not quite as short as the other proof of subversiculi that I gave, but still, I might be able to fit on one board. It is very, very slick. So the way this works is, right. Okay, so you have a bunch of endpoints in the plane, and then you have all these rich lines. So you take all the rich lines you can find and draw all of them. Okay, and so you have a configuration of points and lines, and this is in the projective plane. And then what you do is that you dualize. It's projective duality. And you turn all the points into their dual lines, and you turn all the lines into their dual points. Okay, so just using projective duality, replacing every line or point with basically the orthogonal complement, you get a dual configuration. And in this dual configuration, k-rich lines get turned into k-rich points. Okay, or equivalently, points of degree 2k. If you think of this as a graph or a subdivision of the projective plane into these polygonal regions with line segments, a k-rich line gets dualized into a point which has the degree 2k. Okay, so you have this dual configuration, and what Melchior did was that he just applied Euler's formula to this configuration. So the first theorem in algebraic topology is Euler's formula, which in the projective plane is v minus e plus f equals 1. Well, strictly speaking, if you need the points to not be all collinear, otherwise something degenerate happens. But as long as they're not all collinear, there's enough lines and points that this is actually a valid formula. So you have this formula, and then on the other hand, every edge is incident to 2 faces, and every face is incident to at least 3 edges. Okay, and again, here you have to use the fact that you're not all collinear. So if you just use these facts, put them together, and you double count, it's not hard. Okay, so I did use 2 boards. Okay, didn't quite fit on one board. Pretty soon you end up with the following identity. Euler's formula, after just a little bit of manipulation, ends up looking like this. Nk is the number of k-rich k-rich lines, which dualizes the number of k-rich points. And ms is the number of faces with s sides. So there's at least three sides. And the point is that this is positive, this is non-negative, because s is at least 3. This is non-negative. This is non-negative except when n is 2. And so you can put the n2 on the other side. Okay, and you get that n2 is at least 3. Okay, so you rewrite all those formula in a certain way that emphasizes the positivity of certain things, and then you just extract out the one term that's not actually positive, and you get Melchior's bound. So this is what Melchior did. So maybe I'll do that right now. Right over here. But if you stare at this formula, this is a nice robust identity. That if you know that there's few ordinary lines, then that forces, since everything is non-negative, that forces. So one consequence of Melchior's bound is that if n2 is small, then most nks have to be at 2 or 3. So it's in fact most points in the dual configuration have to have degree 6, because the points of higher degree will contribute too much over here, and most faces have to have 3 sides. Okay. So Euler's formula tells you a lot of structure on your configuration. And so on the projective dual side, what starts happening is that your drawing of all these points and lines must start looking, at least combinatorially, like must have big chunks of triangular hexagonal ladders. Okay, this is basically the only configuration in which every point has degree 6 in every side. Every face has degree 3. Now, so it won't completely be a triangular lattice. It's just locally because n2 is not entirely 0. There's a few places where because n2 is a little bit bigger than 3. There'll be some transitional regions where you transition from one hexagonal grid to another hexagonal grid, and so forth. But the dual configuration must look something like this, and that tells you a lot about the original configuration. See, in particular, the moment you have a shape in the dual configuration that looks like this, this dualizes to a configuration that looks something like this. Okay. How am I going to do this? Okay. So every time you see a picture in the dual configuration that looks like a hexagon, you get, in the original configuration, a collection of 9 points and 6 lines that look like this, as it turns out. And now we can use a very classical theorem in algebraic geometry called the Cayley-Bacharach theorem. That says that if you have a configuration like this, 9 points and 6 lines, which are incident in this way, and if you can find a cubic curve, any curve of degree 3 that passes through 8 of these points has no choice. It must also pass through the 9th. Okay, so this is the Cayley-Bacharach theorem. It's a very nice application of Bezout's theorem. It's not that difficult to prove. You may be more familiar with the special cases of this. If your cubic curve is just 3 lines, this is called Pappus's theorem. If you have 3 lines if you have 2 lines, actually, first of all. If you have 2 lines, and then you draw 3 points on each line, and then you take the 3 points that are incident, then these are also collinear. That's a special case. There's also Pascal's theorem, which is also the special case when your cubic curve is a conic and a line. It's a very similar theorem. So this is the Cayley-Bacharach theorem. So if you use this, what you start seeing is that you can pick 8 points here. You can always find at least one conic going through 8 points just from linear algebra. This is conics have like 10 degrees of freedom in a plane, 10 or 9 maybe. Okay, but it's something more than 8. Okay, so given 8 points, you can find a conic, a cubic going through 8 points, and then if you have a big hexagonal grid in the dual structure, you can keep applying Cayley-Bacharach over and over again, and this cubic curve is forced to pick up more and more points of your configuration. So what you can show from this is that if n2 is, for example, size bigger of n, using the Cayley-Bacharach theorem, you can show that, that your configuration can be covered by bigger of 1 cubic curves. Okay, so this is already a pretty good structure theorem. It's a non-trivial structure theorem. That there's a finite number of cubic curves. So come like this, and then maybe a conic and a line, and then maybe 3 lines over here. And between them, this whole mess of cubic curves cover your whole space. Now, this is, well, this was the first step, but this is still quite far from our full theorem. You can mess around a bit further with Bezout's theorem. It's hard for these a cubic curve and a conic curve, they can't intersect in too many points. And you can rule out a lot of configurations. If you have at least 2 curves that are not lines, you run into trouble. You don't get a consistent decomposition. So if you mess around with Bezout's theorem long enough, what you can show is that, in fact, one of 3 things happen. So P is either going to be covered by a bounded number of lines, or a conic and a bounded number of lines, or an irreducible cubic. Okay, and it turns out that these are actually you can eliminate a lot of the complexity of this configuration. And so then you're in a case where plus maybe a bigger one of the points. Okay, there's some trash in this last case. This is getting closer to the main theorem. The main remaining task is, strangely enough, actually the linear case, where Bezout's theorem is actually not so useful. There's a subproblem where if you already know that your points lie on a bunch of lines, then you need to generate a lot of ordinary lines. You want something of the following form, that if you have, say, k lines, and P has sort of at least epsilon n points on each line, okay, then you should be able to generate a lot of ordinary lines. In fact, we should generate about n squared of them. So there's a key sublemma that you need, that if you have k lines, each of which has a lot of points on it, then it's really hard to make this configuration in such a way that there's very few ordinary lines. And to do this, to eliminate this case, we have to use some tools from additive combinatorics. So I might just talk a little bit about this. There turn out to be sort of 2 main cases. So there's a parallel case, and then there's a non-parallel case, like this. So the concurrent case, where the 3 lines meet, here they meet at infinity, and here they don't meet at all, or they meet at different points. You see, these are sorts of degenerations of elliptic curves, and this isn't a degeneration where we sort of the group becomes the additive group of the reals, and here's where the group becomes the multiplicative group of the reals. So over here, the problem is that there is sort of a counterexample to this statement. If you're allowed to have an infinite number of points, if you're allowed to have if you take an infinite arithmetic progression of spacing 1, I think spacing half here. Okay, if you have, say, three equally spaced lines, and if you take an infinite arithmetic progression here, here, and here, with here having twice the spacing, half the spacing, then there's no ordinary lines. Every line that goes to two of these points goes to a third. So this would be a counterexample. And if there were any finite subgroups of the reals, you could cook up a similar example using that finite subgroup to ruin this lemma. But of course, there are no finite subgroups of the reals. But you need a robust version of that statement. There's not even anything that looks like a finite subgroup of the reals. And this is where some additive combinatorics comes in. Similarly, I didn't prepare the notes here, but if you work out, if this is, say, the line x, y equals 0, y equals 1, and x equals 1, you can work out when 3 points are collinear, when 0, x, 0, a, 1, b, and c, 0 are collinear. And I think it's something like c has to be minus a, b, or so there's some multiplicative relationship between c, a, and b, which I haven't quite remembered right now. But this has the structure of the multiplicative reals. Each of these lines here. And if the multiplicative reals had large finite subgroups, you would again have a counterexample to the statement. And you also need a version of the statement that the multiplicative reals also don't have large finite subgroups, or even anything that resembles a large finite subgroup. And that's more additive combinatorics. And then there's more complicated configurations where you have both parallel lines, concurrent lines, and non-concurrent lines. And then you have to use something called the sum product phenomenon. But you can. And you can rule that out, and then you can finally get to the point where all the points are either just on one line, or on a conic in one line, and or on an irreducible cubic. And then from there, you're already so close to the main theorem that you can basically bash things out by hand. I'll just point out there's one theorem that we use which is very cute. We actually use a nice result of Poonen and Rubinstein, which actually came from Galois theory of all things. So one tool that we actually use is the following: that if you have a unit circle, say, and if you take the nth Lewis unity, and you draw all the chords connecting nth Lewis unity, then there'll be a few points that will be, so there'll be some points that lie on a lot of chords. So kind of the origin will lie on a lot of chords. But as it turns out, if you're not the origin, any interior point, if any interior point on disk is not the origin, okay, lies in at most 7 chords, going with unity. It's a very beautiful paper, actually. It's a nice Galois theory thing followed by a not so nice computer verification. But the idea, at least, is very nice. You can rephrase this as like 2 chords, like three chords are concurrent if and only if I think a certain combination of 12 which unity is similar to 0. And you can start asking start classifying when that happens. So we actually use this theorem. They didn't state it, but there's a version also for exterior points. Every point in the exterior also lies in at most some constant number of chords. For our purposes, we just need a constant, so we use that. And then we have a theorem like this for elliptic curves. Well, okay. So if you take a subgroup of order n on an elliptic curve, and you ask, well, we don't know if it's a theorem of Rubinstein type that any point not on the curve should lie in at most some constant number of chords connecting elements in this finite subgroup. We can't prove that, unfortunately, but we can limit the number of points which lie on a huge number, like on like a constant times n. If the number of points which are incident to like n of 100 chords of this type, we have a bound which is constant. There's at most a big O 1 points of that type. So we have a weaker version of the Rubinstein theorem for elliptic curves, and using those we can prune out a lot of the remaining cases and get down to this final theorem, which actually then gives all the applications. Okay, maybe that's a good place to stop.